Second way of making solutions with a specific molarity is to start with a solution that has a higher concentration, add some water, and make a solution that has the wanted lower concentration, or expressed as molarity. Start with a solution that has some higher molarity, add water, and then get a solution that has the seeked or wanted lower molarity. This process is called dilution. I'm diluting a concentrated solution to make a diluted solution. And to do the mathematics for this process, it's extremely convenient to take the definition molarity equals moles over volume and re-express it as the moles equals molarity times volume, because, hey, I'm going to change the volume, right? And when I change the volume, obviously the molarity is going to change, but I'm not adding, or I can't even subtract. I wouldn't even know how to subtract solute, so I can't change n. N is staying constant all the time. So this way of re-expressing the definition, that turns out to be very advantageous. Okay, here's the artist's perception of what happens. I'm starting with an empty, or just filled with a little bit of water, it doesn't matter really, with an empty volumetric flask, and I'm taking some concentrated solution that I take out of a stock bottle, so I have some concentrated solution in my stock room. That's why it's very often called a stock solution, but it's really just a concentrated solution that I have at my disposal, and I'm using very often a pipette. Pipettes are pretty accurate. This is a graduated pipette. You can read off how much you take directly at the pipette. So the number of moles you put into this flask can be directly calculated by the volume of the concentrated solution. You can read it off at the pipette, and then the molarity of the concentrated solution, which is on the label of your stock bottle. So yeah, you know this. You know the moles you put in the bottle. Then you do the normal dilution process, right? Fill this bottle up, swirl it around, fill it up until exactly to the ring. And then you have a diluted solution. The moles haven't changed, but the volume of the diluted solution is known because it says so on the flask, and the molarity you can calculate now because the moles you know from here, and the molarity and the volume you know from the bottle. Cool. We know the molarity of the solution we made. So let's put it all together. So here's my equation. The number of moles doesn't change, so it's E equal to the moles of the concentrated times volume concentrated equals moles diluted times volume diluted. So really I can cut the moles totally out of the calculation and just take this part, and I kind of put this here into this box. That is the formula I'm going to work with. I don't need to calculate the moles. I can work directly just with this molarity, this volume, this molarity, and that volume. So again, here's my formula. This is the high concentration. As a rule, that's the stock solution. This is the small volume because it comes from the pipette. This is the low concentration. In the lab, that's usually what I want to make. And on an exam or in class, I don't know, any of these might be unknown, but in the lab, this is usually what I want to make. This is my target, right? And then this is the big volume. This is always the volumetric flask. So that's that.